This diagram shows the fuel system of the power plant. Take a moment to familiarize yourself with the controls and components on this diagram. Fuel from the fuel tanks enters this system through a low-pressure fuel shutoff valve and eventually flows through a high-pressure fuel shutoff valve. The low-pressure and high-pressure fuel shutoff valves are normally opened or closed by movement of the master switch. Note, the low-pressure fuel shutoff valve is also commanded closed if the associated engine fire push button is released. The low-pressure pump increases the pressure of the fuel from the fuel tank and sends the fuel through the fuel oil heat exchanger, where the cold fuel is used to remove the heat from the engine oil. After the fuel oil heat exchanger, the fuel flows through the fuel filter. Fuel is able to bypass this filter if it is clogged. After the fuel is filtered, it passes through the high-pressure pump, where the fuel pressure is raised to levels necessary to atomize the fuel for proper combustion. The fuel from the high-pressure pump is divided to flow unfiltered to the fuel metering valve, or FMV, and filtered to the servo fuel heater and the servo valves of the hydromechanical unit, or HMU. Fuel that flows through the FMV must next pass through the high-pressure fuel shutoff valve before it is delivered to the fuel nozzles. The hydromechanical unit, or HMU, contains the actuators and components within the green dashed area. The hydromechanical unit is controlled by the FADEC. The HMU provides some of this high-pressure fuel to operate actuators on the components shown on the right, while the majority of the fuel is delivered through the fuel flow meter to the combustion section of the engine. Therefore, the HMU controls the fuel flow to the combustion chamber, controls the fuel hydraulic signals to the actuators, and protects the engine against an overspeed. Fuel flow information is displayed on the ECAM. The fuel metering valve transforms the FADEC orders through a torque motor and servo valve into fuel flow to the engine fuel nozzles. The FMV resolver generates a feedback signal proportional to the FMV position. The bypass valve maintains a constant pressure drop across the FMV to ensure that the metered fuel flow is proportional to the FMV position. With the engine running, releasing of the engine fire switch will cause only the low-pressure fuel shutoff valve to close. In this case, the engine will continue to run until the fuel in the lines is consumed. On the other hand, with the engine running, moving the master switch to off will command the low-pressure and high-pressure fuel shutoff valves to close, and will also close the fuel return valve and open the bypass valve. This action causes an immediate shutdown. When the engine is running, the FADEC computes the fuel flow that will maintain the target N1. As the FADEC maintains this N1, it allows N2 to vary while remaining between N2 minimum and N2 maximum. The FADEC also controls the engine parameters to limit acceleration and deceleration, avoid engine stall or flameout, limit maximum N1 and N2, and maintain air bleed pressure requirements. The FADEC computes an N2 correction according to the bleed configuration as shown on this simple diagram. Independent of the FADEC, the overspeed governor limits the N2 by opening the fuel bypass valve in the event of a malfunction that could lead to an overspeed condition. The FADEC operates three idle modes when the thrust levers are in the idle detent. These modes are modulated idle, approach idle, and reverse idle modes. Modulated idle occurs on the ground when reverse is not selected, or in flight when the flap lever is at 0. In the modulated mode, the idle speed depends on the demand from the bleed system and the ambient conditions. Approach idle occurs in flight when the flaps are extended, flap levers not set at 0. The approach idle speed is higher than normal idle to allow for faster engine acceleration during this phase of flight. The approach idle speed is adjusted by the current altitude regardless of the demand of the bleed system. The reverse idle mode is selected on the ground when the thrust lever is in the reverse idle position. The reverse idle speed is a slightly higher value than forward idle thrust. Now, some of the fuel from the HMU is delivered to cool the oil of the integrated drive generator, or IDG. IDG cooling is fully automatic, and you'll rarely be aware of its operation. After cooling the IDG oil, the fuel is returned to the fuel pump or to the fuel tank. Take a moment to familiarize yourself with the IDG cooling section of this diagram. The fuel return valve, or FRV, is closed when the engine is shut down and during takeoff and climb, or in flight when the wing tank fuel temperature is above 52.5 degrees Celsius. The FRV is also closed if the wing tank level is below 300 kilograms or 660 pounds, or there is an overflow in the surge tank, or if the fuel is by gravity feed only. When the FRV is closed, the cooling fuel from the HMU is routed through the IDG cooler and then back to the inlet of the high-pressure pump, where it joins the cool fuel flow from the low-pressure pump. Except as noted, the FRV is open and allows the hot fuel that exits the IDG cooler to mix with cool fuel from the low-pressure pump as it returns to the fuel tank. At low engine thrust, if the oil going into the IDG is too hot, the cooling fuel is sent back to the tank at a rate of 300 kilograms per hour. If the oil temperature continues to rise, the ECU or FADEC increases the minimum N2, which increases the fuel flow to some degree. If the oil temperature still continues to rise, the FADEC increases the fuel flow to between 300 and 600 kilograms per hour, depending on the temperature of the return fuel. The FRV mixes the hot fuel from the IDG cooler with the cold fuel from the low-pressure pump so that the temperature of the fuel returning to the fuel tank remains below 100 degrees Celsius. The fuel flow required to do this is about 200 to 400 kilograms per hour. This diagram provides an overview of the IDG cooling fuel flow operation according to temperatures and return fuel flow. This frame shows the EWD messages that are related to the engine fuel system. The advisory message of engine 1 or 2 fuel return valve indicates a failure of the fuel return valve so that it is not in the commanded position. Note, this is inhibited for flight phases 3, 4, 5, 7, and 8. The advisory message of engine 1 or 2 fuel filter clog indicates the fuel filter is clogged. The ECAM engine page automatically displays when this message is displayed. Note, this message is inhibited for flight phases 4, 5, 7, and 8. The caution message of engine 1 or 2 fuel control fault and single chime sound indicates a disagreement in the position of the fuel metering valve, or FMV. The caution message of engine 1 or 2 control valve fault and the single chime sound indicates a burn stage valve failure, or HPTC, or RAC system failure. Note, these messages are inhibited for flight phases 4, 5, 7, and 8. The caution message of engine 1 or 2 high-pressure fuel valve and the single chime sound indicates the high-pressure fuel valve is failed in the closed position. The ECAM engine page is automatically displayed when this message activates, and the associated fault light on the engine panel on the pedestal will be illuminated. Note, this message is inhibited for flight phases 3, 4, 5, 7, and 8. This completes our description of the engine fuel system. Next, to answer some questions.